Hello, everyone, and welcome back to physics class. Today, we're going to be looking at the unit vector. So the unit vector is a special vector, and it's incredibly useful to use whenever you're looking at scaling things, because they can be scaled. So anytime you're making a vector graphic image or anything like that, you're using vectors that are unit vectors. So unit vector is called a unit vector because they have a magnitude of 1. And we often express them as letters with little hats on them. So I'm going to draw just a little example. Say we have this vector A right here, and it has a length of 2.5. The unit vector of 1, magnitude 1, we would denote as A with a hat. So we can express our vector A with this unit vector here. We would just write 2.5, which is the length of the vector A, and we multiply it by our unit vector, which is A with a hat. So this is how we would use unit vectors. So when we use unit vectors, we often like to use unit vector notation, which is just a way that we can write vectors as unit vectors that are along each axis, so the y and the x-axis. When you get to 3D vectors, you would add in your third dimension axis, which is your z-axis. But for now, we're just going to be using our x and y axis. So let's say that we have this vector right here, and we call it vector v. And let's say that the scaling on the x-axis is going up by 1, and the scaling on the y-axis is going up by 3. We can express this in vector notation just by the information that we've been given here. So, before we get started, something important to note. The horizontal component along the x, the unit vector we use is I with a hat. And then for the vertical component, which is the y, we use the letter J with a hat. So this is very important to remember. So if we wanted to write vector v in terms of vector unit notation, we would go ahead and write out our unit vector for the horizontal. So remember, the unit vector is your I, and we would multiply it by the length of the horizontal component, which is 2. So then it becomes 2I. Then we would go to write about our j. So if we draw in our vertical component, we can see that our vertical component is 6, positive 6, and we want to multiply it by the unit vector, which is j. So this is our final answer, and that's how we write it in unit vector notation. I'd like you to take a moment and try it out yourself. So I'm going to draw this right here. So this is -3, -6, -9, -1, -2. So let's say we have this vector w right here. I want you to write this vector w in unit vector notation. So take a minute, pause the video, and write it out. All right, so let's get started. We set out with our W. Now we want to measure the horizontal. So we know that the horizontal vector is -2 I, because the horizontal will always have the I. And then the vertical vector would be -9j. And then that is our final answer for the unit vector notation. Now, those were examples with a graph where you could visually see your vector and the different components. But sometimes you might be given the vector components themselves. So let's say we have Vx is equal to 5 meters per second, and we have Vy is equal to 7 meters per second. We want to write this in unit vector notation. So vector V, in this case, would be equal to 5I, because remember we take this, and for the horizontal would be an I, plus 7j. Now the reason why I put this in square brackets here is because the unit is going to come to the outside. So whenever we write something that has a unit, we would always include the square brackets, and the unit would be on the outside. So let's take a moment and try it out yourself. Let's say you have f of x is equal to -10 newtons, and f of y is equal to 18 newtons. I want you to pause the video, take a moment, and try writing this out in unit vector notation. All right, so the final answer for this question would be this. Vector f is equal to -10 with our I. This is a positive 18, so it's plus 18j. And we would finally bring our newtons, our unit, to the outside. Like that. Now, here's another example. This time, we have a vector that has been given us with a direction. It's not on a graph. We don't have the vector components. We've been given the total vector. So we need to actually calculate the vector components and then write them in unit vector notation. So if we recall, our formulas for fx or vx would be f cosine theta, and then fy would be f sine theta. Those are for our vector components. So let's do some quick calculations here. F of x is equal to 100 cosine my angle, which is 200. When I put that into my calculator, again, making sure that my calculator is in degrees, I would get negative 94 newtons. Calculate my Fy would be 100 times the sine of 200. I would get an answer of negative 34.2 newtons. So I now have my x and I have my y. It's time to write out my unit vector notation. So my vector f is equal to negative 94I minus 34.2j newtons. Now I'd like you to try it yourself. Write the following vector in unit vector notation, where your vector is 10 meters per second at an angle of 50 degrees. Take a minute, pause the video, and try to calculate it yourself. All right, let's go over this. So we first need to break it up into our components. So we write out our formulas. And then we go one at a time. So let's calculate our Vx first. So 10 times the cosine of 50. This will give us positive 6.4 meters per second. Then we calculate our Vy. So 10 sine of 50. And when you calculate that one, you should get positive 7.7 meters per second. Finally, the last step is to write it in unit vector notation. So our vector is equal to 6.4 I plus 7.7 J meters per second. Thank you for listening, and I'll see you next time when we talk about going backwards, finding the magnitude and direction from vector components and unit vector notation.